I would like to ask Arianna Minoretti, who was the convener of the bulletin, to give us the first presentation that will go on the chapters 1 and 2 introduction.
Thank you, David. First of all, I have to thank Akio and Turuli for their introduction. I have to say that I always learn something new every time I hear Turuli speaking, and I really find fascinating the history regarding these structures, the floating structures, and to hear what the new technology allow us to do today. So my name is Arianna Minoretti. I'm chief engineer at the Norwegian Public Road Administration. And as David said, I had the honor to be the convener for this working group. I take the opportunity to thank all the authors for the precious work. They've been amazing. And I'm glad that many of them are participating today to present part of their work. So I will start, of course, from the beginning. Let's see if, okay. Yeah, it's working now. So that means from chapter 1 of the guideline. The chapter 1 is the shortest chapter of the guideline, but it is very important. Chapter 1 defines the scope and the limits of the entire work. The scope of the document is to provide guidelines for the engineering community on the design and construction of a submerged floating tube bridge, based on relevant experience. So for this reason, during the presentations of the chapters, the authors could refer to specific studies they have been involved in. The second important concept mentioned in chapter 1 is the topic of the guideline. First of all, the submerged floating tube bridge is a type of structure for general use, we say, but this document focuses on concrete structure for traffic. Chapter 1 ends with a sentence that summarizes I would say, the spirit of this working commission. This is one of those short sentences that it takes hours to write. So that's why I will read it directly from the guideline, because there is no way to say it in a better way, I think. The working party aims to improve the knowledge of the scientific community on submerged floating tube bridges, helping them in the design process and strengthening the confidence of the community on a type of structure that has a great potential. So we go on with the chapter 2, that is called the Submerged Floating Tube Bridge. Let's start from here. What is the Submerged Floating Tube Bridge? Here is an old video from one of the studies for the Norwegian fjords that was done for the Sognefjord. That is one of the widest and especially deepest fjords in Norway. The Submerged Floating Tube Bridge, or SFTB, we call it, is a tube bridge submerged but floating at a defined depth under the water surface. The structure behaves like a bridge, being exposed not only to static but also to dynamic loads. So the shape of the structure for the users can recall to the idea of a tunnel, and that is also why it is also called submerged floating tunnel. But from the point of view of the behavior of the structure, it is a bridge. As every submerged structure, it is subjected to an uplifting force called buoyancy that is proportional to the mass of the displaced water. As we will see in the following part of the presentation, this gives a huge opportunity in the design to use the Archimedes principle to counterbalance the vertical loads. In this picture, it is easier to understand the differences among the different type of crossings. I think you can see, yeah, my pointer. So from the bottom, you can see an undersea tunnel that is passing under the water basin. Then you have an immersed tunnel that is laying on the bottom of the water basin. And then you have a bridge up here in the upper part of the drawing. And finally, here in the middle, a submerged floating tube bridge that is floating, immersed in the water. So for deep and long crossings, longer than, let's say, 1 kilometer, more or less, a vertical stabilizing system has to be provided. These can be done by floating pontoons, for example, as in the picture up left, or with tethers connecting the structure with the seabed, as in the picture up right. For shallow crossings, a column system could be used, while for short crossings, a free span bridge could be planned, as shown in the bottom right picture. It is easy to understand that all these different solutions has pros and cons. And generally, we can say that the submerged floating tube bridge is a very flexible system because it is able to adapt to different situations and challenges. So for a situation where the geotechnical conditions of the seabed are unreliable, for example, or where, for example, there is the possibility of landslides that could compromise the foundation system, a solution with floating pontoons could be more favorable. The pontoons are the same structure used for floating bridges, and with this component, the structure is directly exposed to the wind load, even if just partially. Of course, having elements floating on the water surface will also expose the structure to the risk of collisions. So for example, with passing vessels. So these must be taken into consideration in the design, and specific analysis must be performed. But this collision risk can also be managed, developing adapting strategies, we can say, for the specific structure. So in the Bjornafjord study done in Norway, for example, in case of a collision with big vessels, the system connecting the pontoon with the twin tube bridge was able to interrupt the transmission of the load, avoiding to overload the structure. Of course, this means that the pontoon must be replaceable and that all the related operations must be defined and calculated in the design. But if we have a situation where a free passage of vessels is preferable, then a solution of a submerged floating tube bridge with tethers that are connecting the structure with the seabed could be an alternative. This implies a sufficient knowledge of the local geotechnical conditions and it needs to perform reliable subsea investigations. This solution will avoid collisions with floating vessels, but in case of presence of submarines, for example, specific analysis of the collision effects must be provided. The submergence of the structure serves not only the purpose of avoiding surface collisions, and usually we can say that a draft of 20 meters is enough to exclude this possibility, but the submergence is also reducing the main sea load on the structure. And this happens in a, I would say, natural way due to the fact that as you can see in the picture where the trend of the wave load is with the water depth is shown, the more the structure is submerged, the lowest load the structure will have to face. So this is a huge difference from the oversea bridges that are fully exposed to the loads, think about the wind load, for example, and there is no way to reduce the acting load on the structure. So you can apply several strategies on the structure, but there is no way you can change the incoming load. So for this reason, the Submerged Floating Tube Bridge could be a competitive structure for crossings that are severely exposed, maybe being the only possibility to have a zero downtime crossing. So a crossing, we can say, always open. And this makes a huge difference when you have to justify to the public the economical investment to build a new bridge, a new crossing. This is not the only advantage of this structure. So imagine the possibility to build a hidden crossing, preserving the landscape, saving space on land, actually as you can do with a tunnel, but with the possibility of locating the structure just some 10 meters under the water level. So reducing the length of the crossing and avoiding the problems related to the road gradient that you usually have when you design the access, for example, for a subsea tunnel. So we could say that this structure combines the advantages of tunnels and bridges, giving new unforeseen possibilities for several crossings, I would say. Also from the environmental point of view, there are some aspects that deserve to be mentioned. As for tunnels, the acoustic impact for this type of structure is beneficial if we think about the surroundings and also the land fauna. But what about the effect on the sea species? Among the environmental issues that need to be investigated, the underwater noise pollution produced by the Submerged Floating Tube Bridge and its possible effect on marine life needs to be carefully evaluated in early design stages. And this in order to define the best mitigation choices and procedures. So this implies not only an analysis for the construction period, where we already know there is the possibility to schedule the operations, avoiding the periods where the environment is more sensitive, but also an evaluation of the long-term effect of the structure, considering that the vibrations of the structure are translated into sounds for some sea species. And this is not just a matter of sound. The general environmental impact needs to be evaluated, both in terms of biological impact and in terms of climate gas emissions, for example. So this must be done from the early stage of the project to guide the design choices and define the best mitigation strategies. The evaluation of the environmental impact could affect several aspects of the bridge, from the geometry to the choice of the materials, also to the detailed technical solutions. On the reliability of the concept, the Submerged Floating Tube Bridge is an old concept, proposed for the first time in the late 19th century. The idea has appeared in the last century for some proposals, but the necessary technology for the seabed connections and the marine operations has been developed in the offshore field in the 80s. So, well, for the history lovers, there is a TEDx available on the web on the story of this structure. But what is important to know is that nowadays, after nearly 40 years of applications, we can think to apply this technology also to the transport field. So This is a picture on the development in the offshore field that Tor Ole showed also before. For example, the tethers, those elements that you can also see during the towing and installation phases on the right part of the picture, were applied from the 80s in the tension leg structures technology. And these are the same elements that we consider in the design of the SFTBs for long and deep crossings. And in the recent years, many tests, simulations, and validations procedures have been performed, and many results have been published in scientific publications. So I can say that this knowledge is available for all the scientific community. Well, actually, we have to say that in these years, two hybrid solutions have been constructed. One in Norway in the 80s, and is the structure that you see in this picture in 1982 in Korstø in Norway. Actually, this structure was constructed not for traffic purposes, is a concrete SFTB actually, but the scope of the structure was to protect two gas pipeline. It was a 600-meter bridge on these elements, sort of columns. But this structure shows that the technology and the marine operations that are needed to build such a type of structure were available already in the 80s. And the other structure is the Söderström tunnel. This was built in 2015 in Sweden. This structure is designed for traffic, but technically it is a subsea tunnel. But the fact that, if you can see in this picture, this structure is relying on group of piles. So it makes it behave from the static point of view as a submerged floating tube bridge. Tor Ole will mention again this structure when at the end of the webinar, when he will present chapter 14. So after having understood the topic of the guideline and the scope of the document, we go deep into the design process. These are the chapters of the guideline, and we are going to present all of them briefly today. I have presented the introduction and the second chapter on the presentation of the submerged floating tube bridge. Then we have a chapter on rules and regulation, a chapter on functional requirements, and then we have two chapters that are really connected: site condition and actions and action effects. Then we have chapter 7, one of the core chapters on design principle. And then we have two important chapters that are also really connected: construction and installation. Then we have chapter 10 on mechanical, electrical, and plumbing system. Chapter 11 on operation and maintenance. Then we have chapter 12 on risk and reliability. And then the last two chapters on cost, and the last chapter that will present briefly some studies, some main studies on the submerged floating tube bridges presented on this structure.